Okay, we're going to continue with a new lecture. This will be the Chemistry of Life, Part 4. And in this lecture, we're going to explore a few issues, but they're related to one another. In each of the slides, we're going to explore what happens when you dissolve something in water, or you attempt to dissolve something in water. We'll look at what happens when you put a salt in water, what happens when you put something that's like oil in water, and what happens when you put acids and bases in water. And so this is the Chemistry of Life, Part 4. On this slide, we're going to figure out why some molecules or why some substances can dissolve in water. And the substance that we're going to use here, the example that we'll use would be sodium chloride. Let's start out here with a sodium. We're going to start out with a sodium cation. Sodium, and then the chloride anion. Okay. Cl minus. And so this is sodium chloride. Okay, it's kind of big here, so let's make it a little smaller. So here we have sodium chloride. Now, sodium chloride, it is a salt. It has a positively charged cation and a negatively charged anion. How does something like this dissolve in water? Okay, let's make ourselves let's move this up here. I'm going to move it over here out of the way. And then we're going to create ourselves. We're going to duplicate this one and move it here. And so when it goes in water, something happens. You put this in water, something happens to it. The sodium and the chloride separate from one another, and we call this process dissociation. So what happens? The sodium and the chloride, they separate from one another, and this is called dissociation. Now something happens to keep these two entities apart. Okay, let's get ourselves a water molecule here. And so in water, of course, you're going to have a water molecule. Okay, we're going to have the oxygen atom, and we're going to have the hydrogen atom and the hydrogen atom. Okay, and over here you're going to have your partial positive, and where the oxygen is, you're going to have your partial negative charge. Okay, and there's your oxygen atom. Now I could draw all of these oxygen atoms this way, or all of the hydrogen molecules this way, but it's going to take a long time. So in the future, I'm going to draw all of my water molecules. I'm going to draw them like this. Okay, and this symbol will represent water. Okay, there's my oxygen atom, and here's a hydrogen, here's a hydrogen, and each of them is going to have a partial charge. And so what I'll do here, I'll just put here for the oxygen atom, it has a partial negative charge, and for the hydrogens, they have a partial positive charge. So this little red, blue, and yellow symbol, this is a water molecule. Now, how is the sodium ion dissolved in this water? Okay, Let's go back. Okay, and so what's going to happen here, because the sodium has a positive charge, the partial negative charge on the oxygen atom, it is going to orient itself towards the sodium atom. Okay, it's going to orient itself there. Okay, and then you're going to have a water molecule here, a water molecule here, a water molecule here, and a water molecule here. So you're going to have lots of water molecules around this sodium cation, but all of them will orient their negative charge towards, all are going to orient their negative charges towards the positive sodium. And so they're going to be, in essence, they're going to make a shell of water molecules. They're going to make a shell of water molecules around this sodium, ion. Okay. And this shell, since it's made of water, this shell of ions around this sodium ion, this shell is called a hydration shell. Okay. And so here we have a hydration shell. Okay. DRATION, a hydration shell. And this hydration shell, this hydration shell allows sodium, the sodium ion, to dissolve in water. Okay. And on the next slide, we're going to find out what happens with the chlorine anion. We're going to figure out how the chlorine anion is dissolved in water. Okay, we've explored how the sodium cation is dissolved in water. On this slide, we'll look at the chloride anion. We're going to let us move our water over just a little. Okay. Let's move this. Let's move our height. Actually, let's do something here. I want to move the water over. Oop, not everything. Just the water. I want to move the water over. Well, I want to move the water and the sodium. Move both of those over. The water and the sodium. Let's move both of those over. Okay. Kind of move everything over. Excellent. Now what we're going to do here, let's put another hydration shell around the chloride anion. So let's just make a copy of this one and move it around the chloride anion. And this is now we have a hydration shell around chloride, with the exception that the negative charges are oriented towards the negative charges, and that cannot be. And so let's do this. Let's reorient this hydration shell, or reorient the water molecules so that the positive hydrogens are oriented towards the negative chloride. so here we're orienting the partial positive hydrogens towards the chloride anion. And now we have a hydration shell around chloride. And this is what happens when water is dissolved in water. The first thing that happens is that the two ions, the sodium cation and the chloride anion, separate from one another. And that separation is called dissociation. It's called dissociation. That's the name of that separation. Okay. The positively, both together, both of these together, when you have a positive cation and a negative anion, we call that a salt. We call that a salt. Unless the cation is a hydrogen cation, we call it a salt. Let's see here. And so we have a hydration shell. Whenever you have a substance that has a positive charge or a negative charge, or strong partial positive or strong partial negative, we call that substance a polar substance. And so as we can see here, sodium chloride is very polar. Also, water has a strong partial positive, strong partial negative. So water itself is polar. So sodium chloride is polar and water is polar. And because sodium chloride is polar, it can dissolve in water, because water can make a hydration shell around it. Any substance that can dissolve in water is given a special name. We call such a substance hydrophilic. Let's zoom in here so we can see this. Hydrophilic. Hydro means water, and the root word philic means love or loving. So any substance that can dissolve in water loves water, like sodium chloride. It can dissolve in water, so it's hydrophilic. Sugar can dissolve in water, so sugar would be hydrophilic. Let's see what else likes to dissolve in water. Something like, I guess, like alcohol. Alcohol can dissolve in water. It's hydrophilic. Something like vegetable oil. Vegetable oil does not dissolve in water, so it's not hydrophilic. And we'll learn later on the name or the label given to substances that don't dissolve in water. So, as a review, here we have sodium chloride, which is a salt. It has a positive cation and a negative anion. When you put sodium chloride in water, the two ions dissociate or separate from one another. And what happens, then you have the sodium cation by itself, and the water molecules orient themselves so that the partial negative of the oxygen is oriented towards the positive sodium cation. And it creates a shell of water around the sodium cation, and we call that shell a hydration shell. And the same thing happens around the chloride anion, with the exception that the water molecules orient themselves so that the partial positive hydrogens orient themselves towards the negative chloride anion. And so here we have two hydration shells. In this process by which water dissolves another substance, that process is called, I don't know if you need to know this, but we'll put it here, solvation. No, you don't need to know that. So that's what we have here. So here we are, hydration shells. Okay, we've talked about substances that can dissolve in water. Now let's talk about substances that do not dissolve in water and why they don't dissolve in water. Let's start with something that we know does not dissolve in water. Okay, here we have a bottle of vegetable oil. Now, if you take a bottle of vegetable oil and you put it in water, just make ourselves a glass of water here. Okay. Here we have a glass of water. That doesn't have to be so crooked. Okay, here's our water inside. Okay. Let's make sure we can actually see the water here. It's kind of dark. Okay. Let's give the water a little color. Okay, there's our water. Now, if you put the vegetable oil in the water, let's make our vegetable oil like an orangish color. Now, what's going to happen? When you first pour the vegetable oil into the water, it's going to go into the water, and it's going to mix all around in the water. The vegetable oil is going to mix all around in the water. But eventually, what eventually is going to happen, that vegetable oil is going to start to accumulate on the top of the water. I don't know if I can represent this. The vegetable oil is going to start floating to the top of the water. It's going to start floating. It's going to be really hard to show. Okay, it's going to start floating to the top of the water, and eventually, what's going to happen here is that the vegetable oil is going to start to settle on the top of the water. You're just going to have a layer of vegetable oil right on top of the water, and it's not going to dissolve. It's not going to dissolve. And now on this slide we're going to talk about why does the vegetable oil not dissolve in water like salt does. Okay, and the reason, it's kind of a simple answer here. I'm going to show you just an example of we're going to show here an example of a fat. I guess we can make it kind of this color. Okay, what happens, let me just show you the fat that's in your body. The fats that are in your body are made up of a 3-carbon compound. I'm not going to draw the whole structure. These 3 carbons are linked together. And attached to that 3-carbon compound are lots of other carbons. Lots of other carbons. And none of these carbons are polar. None of them have a charge. None of them have a partial charge. They're just all non-polar. So if it doesn't have a charge anywhere or a partial charge anywhere, we say that this substance is non-polar. And because it's non-polar, water can't make a hydration shell around this anywhere. And because water can't make a hydration shell around this substance, it does not dissolve in water. Okay? And this substance will not dissolve in water. And so we give a name to substances that don't dissolve in water. And so we learned before the substances that can dissolve in water, we call those substances hydrophilic. But substances that cannot dissolve in water, we call such substances hydrophobic. Hydrophobic. Okay. Now hydro, as we've learned before, hydro means water, just as before. And the root word phobic means hate. So it hates water or fear. Okay? And this is why substances like oils and fats, this is why they don't dissolve in water, because they don't have any polar regions. They don't have any charges anywhere. So only substances that are polar, which means they have partial charges or full charges, can dissolve in water. And substances that cannot dissolve in water, we say that they are hydrophobic. Okay, on this slide there is a term I want to emphasize. I think we've already talked about it, but we do want to emphasize this term. Let's start out with a sodium chloride molecule. So here we have sodium, the sodium cation, and we have I think we've always make this in green, the chloride anion. Okay, and let's get ourselves a glass of water. I'm going to make kind of a big glass of water. Here's our glass of water here. Okay, there's our glass of water. I wish need another color here. Need my water to be not so bright. Okay, now let's give a color to our water here. That's not going to work. Okay, now let's give our water some color. Okay, so here's our water. Now what's going to happen is our sodium chloride when the sodium chloride, when it's outside of water, the sodium chloride is going to be a crystal. It's going to be a white crystal, and we're all familiar with what table salt looks like. What's going to happen, the sodium chloride, when you put it in water, let's put the sodium chloride in. I'm going to have to make them, actually let's go back here. I'm going to make this smaller because it's kind of too big to make the point, because they're so big right now they can't separate from one another. Okay, so let's make the sodium chloride molecule smaller. Okay, there's sodium chloride. Okay. Now, the sodium chloride, let's put it in water. So outside of water, it is a crystal. But now when the sodium chloride goes into water, what happens? The sodium and the chloride, they separate from one another. Okay, I'll just do it this way. They separate from one another. And all I want to show on this slide is the name of that process. That process by which ions separate from one another, that process is called dissociation. Dissociation. dissociation, not disassociation, just dissociation. Okay, and so dissociation is the process by which salts or ionic molecules separate from one another. And that's all I have to say on this slide. Okay, students, on this slide we're going to look at another substance that can dissociate, but it's not a salt. It'll look like a salt, but it will not be a salt. Like sodium chloride is a salt, but this substance, the cation, is going to be different. Let's see here. Here we have H plus, and we can also have OH minus. And we know what this is. This is water. You can think of water as two substances, a hydrogen cation and an OH anion. You can think about it like that. And what's going to happen, since water is already in water, it's already in itself, water can spontaneously, that means without any interference from anything else, water can spontaneously split itself or dissociate. I'm going to make this a little smaller. Water can spontaneously dissociate into its two components. And so let's take these two here. Let's take these components here and we'll just put them up here. Let's separate them, because we're going to name all three of these components. Okay, there we are. And so water can spontaneously dissociate into the hydrogen ion and the OH ion. Now let's name these three components. Of course, this one here, and all three of these would be in a glass of water. This is just the water molecule. So in a glass of water, you have lots of water molecules. You're going to have these hydrogen ions. And so this is a hydrogen ion. I'm going to give this three names. This is the hydrogen ion, but because it has a positive charge, we can call it the hydrogen cation. Okay, and we're going to give it its third name in just a second. Okay. And over here we have, we can call this the OH ion. We can call it the OH ion, or we can call it the OH anion. Okay, people very rarely call it either of these, so they normally call it the hydroxyl ion, or they can call it the hydroxyl anion. Okay, this is the more common name, because if it's hydroxyl, it's understood. If you say the hydroxyl ion, you know that it has to have a negative charge, so that's the more common name. Okay, and this here, this hydrogen cation, is usually referred to as a proton, because it's simply a proton that has lost the electron. This is the common name for this one. Okay. And so in water, we have all three of these components. So if we have ourselves let's give ourselves a glass of water here. In this glass of water, we're going to have all three of these components. We're going to have the water molecule itself. We're going to have protons, H+, and we're going to have hydroxyl ions, OH-. Now the concentration of hydroxyl, well, I'm going to change the order of these. Okay. Okay. Now let's put these here. We're going to have OH-, we're going to have H2O, and we're going to have H+. Now in pure water, the concentration of hydroxyl ions is going to be 1 × 10⁻⁷ molar, and that's going to give it a pH. It's going to give the water a pH of 7. And in the proton concentration is also 1 × 10⁻⁷ molar, and that's going to give it a pH of 7. So water has a pH, pure water has a pH of 7. Okay. Now any substance that you add to water and causes water to create, either it causes the water to create more protons, or that substance that you add to water creates more protons, such a substance is called an acid. So acids create more protons, lead to more protons. If a substance creates more hydroxyls or takes away protons, we call such a substance a base. So bases give you more hydroxyls, or they give you fewer protons. An acid gives you more protons, or they give you fewer bases. Okay, and we're going to stop there on this slide, and we're going to come back to this slide and talk about a scale that you can measure acidity and basicity. Okay, let us continue where we left off. We were talking about the water molecule. The water molecule can spontaneously dissociate into protons, which is H+, and the hydroxyl ion, which is OH-. So in water, in a glass of water, you'll have all three components. You have the water molecule, hydroxyl ions, and protons. If a substance, once added to water, creates more protons, we call that substance an acid. If a substance, once you add it to water, creates more hydroxyl ions or fewer protons, we call that substance a base. Okay. Now there is a scale which we use to measure how acidic something is, or how basic it is. That scale is known as the pH scale. The pH scale. Now if something becomes, the pH scale goes from 14, the highest, down to 0. If something is very basic or alkaline, so up here, if something is basic, which means that it's a base, or alkaline, which means that it's a base. Its pH is approaching 14. If something is acidic, its pH is closer to 0. And if something has a pH right in the middle, pH of 7, that's going to be the pH of pure water. So an acidic substance has a low pH, which means that there are a lot of protons here, because that would be 1 times 10 to the 0 molar, and that would mean you have a 1 molar solution. And if the pH were very basic, that means you have very few of these. So it would be 1 times 10 to the negative 14, the lowest that it can get. So this is the pH scale. So just to represent that again, if you have a pH, if the pH is greater than 7, we have a base. If the pH is less than 7, we have an acid. And if the pH is equal to 7, we say that the substance is, the solution is neutral. Okay? And this is the pH of pure water. Pure water has a pH of 7. Okay? And that's it for pH. So here you have the water molecule. The water molecule spontaneously dissociates into proton and the hydroxyl ion. And so dissociation can occur with water just like with a salt. And so this process, as we've already talked about it, it's called dissociation. Now in water you have all 3 substances: the water molecule, the hydroxyl ion, and the proton. So if the proton, if you add something to water that increases the proton concentration, that is an acid. Or if you add something to water that decreases the hydroxyl ion concentration, that's an acid. If you add something to water that increases the hydroxyl ions or decreases the protons, that is a base. So if something has, so the solution would be basic or alkaline. If the pH is above 7, if the pH of the solution is above 7, then the solution is basic, and the substance you added is a base. If the pH of the solution is below 7, the pH of the solution is acidic, or the substance that you added is an acid. And if the pH is 7, the solution is neutral, and you just have pure water. Okay? And that is it for pH. And on the next slide, we're going to look at some examples of some common substances and their pHs, some common acids and some common bases, and what their pHs would be. Okay, on this slide, we're going to look at the pH of some common substances. We're going to make ourselves, we're going to put the pH values along the top here. This would be 0 to 1, 1 to 2, 2 to 3, 3 to 4, 4 to 5, 5 to 6, 6 to 7, and we're going to put 7 to 8, that's fine. 8 to 9, 9 to 10, 10 to 11, 11 to 12, 12 to 13, 13 to 14. Okay? And for these, so there'll be nothing in these two boxes here. So let's just, let's get a good color to get rid of those. So nothing will go here. Okay. Okay, let's start right in the middle. pH of 7. pH of 7. Now these, I found some images on the internet, but they're kind of blurry. So this is water. Pure water has a pH of 7. And so we will put water here. Pure water has a pH of 7. Now let's get more acidic. And so with a pH between 6 and 7, we have milk. Milk has a pH between 6 and 7. So milk is more acidic than water. And more acidic than milk, we have bananas. Bananas have a pH between 5 and 6. So here we have bananas. Bananas are more acidic than milk. For pH, we won't worry about that one yet. We're going to skip the pH between 4 and 5. Let's go ahead and, I guess we can go ahead and shade it here. Let's see here. We won't consider this one. So we won't do between 4 and 5. We won't give an example of that one. But between 3 and 4, we have oranges. Oranges have a pH between 3 and 4. And so we'll put oranges here. And for the pH between 2 and 3, we have lemons. Lemons are more acidic than oranges. They have a pH between 2 and 3. And the most acidic substance at which we will look is going to be battery acid. This is a car battery. I know it's hard to see. Battery acid has a pH somewhere between 1 and 2. And for the very last substance here, we won't even do a pH between 0 and 1. Okay, now let's find things that are more basic than pure water. Okay. The first substance will be eggs. Eggs have a pH between 8 and 9. So here we have eggs. Even more basic than eggs is bleach. Bleach has a pH between 9 and 10, depending on the concentration, of course. More basic than even bleach, we have ammonia. Ammonia has a pH between 10 and 11. More basic than ammonia, and our last substance is oven cleaner. An oven cleaner has a pH between 13 and 14. And we won't even look at anything that has a pH between 12 and between either 11 and 12 or 12 and 13. So we can just go ahead and shade those out so there'll be no confusion here. And so here we have substances, common substances, and their pH. Again, you can only determine the pH when you put something in water, when you actually put it in water. So as a review, water has a pH of 7, between 7 and 8, more of 7. Pure water has a pH of 7. More acidic than water is milk, and then bananas, then oranges, then lemons, and then battery acid. More basic than water are eggs, bleach, then ammonia, then oven cleaner. And these are some common household items and their pHs.